Hello to all who are watching and to us particularly Mr. Siegel. This is video 1 of 4 of the final physics project. So, without further ado, let's get to it. A train car of mass m1, initially moving at speed v1, moves along a frictionless track and collides completely inelastically with a train car of mass m2 that is initially at rest. Initially at rest, it tells us that it's going to be 0. So let's dissect this before we go into any of the problems. What is an inelastic collision? An inelastic collision is when two objects collide. Well, in this case, two objects collide, and after the collision, both objects stick together, meaning that they move at the same direction, in the same direction at the same speed. The formula for this looks like m1 v1 plus m2 v2. So that's the first mass and the first initial velocity plus the second mass times the second initial velocity. And that equals the first mass plus the second mass times the final velocity. Now, different from an elastic collision where the two objects bump together, these stay together and travel at the same speed. So looking at the picture, we can get a better image for what this looks like. So in the before the collision, we see that the first mass the first train car of mass 1 is moving at its own velocity, so v1 initial. The second boxcar, which has a mass 2, is not moving at all, so its velocity is 0. That's going to be something important to remember for the problems moving forward. Afterward, however, both boxcar of mass m1 and m2 are moving in the same direction at the same speed. So now, this is where we get to the questions. Is momentum conserved in the collision? Yes. And how do I know this? Well, we know this because let's think of the term. First, we have to define what conservation of momentum is. Conservation of momentum is when there are no external net forces acting upon the object. For example, something like friction or something like tension. In this case, there are no external forces acting upon the object. Um, we can see that it's moving along a specifically frictionless track. So everything that's happening between the cars, the train cars, is only happening internally. So M1 is hitting M2, and that is part of the internal system. It is not part of the external system. It is an isolated internal system. So now we understand why the answer is a resounding yes. 1b. In terms of m1, v1, and m2, calculate the final velocity formula. What is the final velocity formula? Let me start over there. In terms of m1, v1, and m2, calculate the final velocity. Again, we see the formula m1 times v1 initial plus m2 times v2 initial equals m1 plus m2 vf. In this case, remember how I said to remember that v2 is equal to 0. The second term cancels because m2 times v2 initial is going to equal 0 if v2 initial is 0. So we're left with the term m1 times v1 equals m1 plus m2 times vf. So our final velocity, we do some quick math, isolate the final velocity, and we end up with m1 times v1 over m1 plus m2. Something important to remember here, we should keep on to this final velocity moving forward to 1c because it's important to remember that the final velocity substitutes for this. Now, moving on to 1c. In terms of those same variables, state how much kinetic energy was lost during the collision. Okay, so what is the kinetic energy? This is something important to look at. Kinetic energy is specifically studying the energy of motion. So we're looking specifically at the motion before the boxcar and after the boxcar, meaning that we're not going to be looking at the second boxcar, which is not in motion, but we will be looking at the whole system afterward and the system of the one box cart before to see how much energy was lost. So what is the equation for kinetic energy? Something we went over pretty exhaustively in physics is that kinetic energy is equal to 1/2 mass times velocity squared. So that means our initial kinetic equation is looking at specifically the first box cart, because again, the second box cart wasn't moving. And going back to the image, we have to look at the moving first box cart. Is so the kinetic energy for that box cart is going to, before the collision, is 1/2 m times v1 squared. The final kinetic energy, so that's going to be after the collision has taken place, is going to be Ke equals 1/2 m1 plus m2 times vf squared. No, now something important to know. Why do we do m1 and m2? That's, somewhere someone could easily get tripped up and think it was just one of the masses, or that they had to multiply the masses. But why add the masses? Because we have to add both masses to get a bigger picture for the entire system. We have to make sure that the system works. So in adding m1 and m2 and multiplying it by the final velocity squared, we are able to get that final kinetic energy. Now remember, what we found in 1b is that Vf is equal to m1 times v1 over m1 plus m2. So our final kinetic energy is going to equal 1/2 m1 plus m2 times m1 times v1 over m1 plus m2 squared. Okay, this is where we find find the lost kinetic energy. Remember, we're not finding the final or the initial kinetic energy. But we need both to figure out how much kinetic energy was lost. So, how do we find out how much kinetic energy is lost? Well, we need to look at use simple subtraction to find the difference between the initial kinetic energy, so the kinetic energy of before the collision, and the final kinetic energy, or the kinetic energy after the collision has taken place. That will give us how much kinetic energy we have lost. So, doing quick maths, we can figure out that the kinetic energy lost is 1/2 m1 times v1 minus 1/2 of m1 plus m2 times m1 v1 over m1 plus m2 squared. So there you have it. That is 1A, B, and C. More videos on the way, and I think I covered everything. So yeah, look forward to that. And one last thing, just a quick typo looking back on this video. The V term should really be squared, so apologies that wasn't written in. Just a minor error. So it really should be 1/2 m1 times v1 squared minus 1/2 m1 plus m2 times m1 times v1 over m1 plus m2 squared. So remember this term squared. Thanks again.